Okay, so we finished the morning session talking about the zip function or pairing two lists, and now we are going to use that operation of pairing lists to create dictionaries. So dictionaries not only exist physically, they are also inside many applications and computer programs that we use nowadays, and they are a really important tool for us to manage data. And for instance, when we are using Google Translate, obviously there must be some sort of dictionary inside the computer with the translations of the words. Now, we will consider as an example a Portuguese-English dictionary, meaning that we go from words written in Portuguese to words written in English, okay? For example, in Portuguese, the word gato means cat. So in that dictionary, we have gato, and then we may put an arrow, meaning that the translation of gato is cat. And to remind you, on the computer, we use quotation marks to represent words. Okay, so these are strings. When we use double quotation marks, we have strings. Okay, and why do we use quotation marks? Why make that distinction? Because there is a difference between a thing and the word that represents that thing. For example, Porto is a city in Portugal which has more than 200,000 inhabitants. But Porto, with quotation marks, is a 5-letter word. Okay, so it's a word with 5 letters. So one thing is like the actual physical city, and the other thing is the word that represents the city. So whenever we use quotation marks, we are talking about words. It's a string. Okay, so suppose that we have a list with some Portuguese words. You're given by Portuguese equals gato, casa, ovo, and raposa. And then we have a list with their English translations, which are cat, house, egg, and fox. When we write something equals something, it means that we are giving a name to that thing. So here we are just saying that we are going to call this first list Portuguese, and we are going to call the second list English. Okay? So let me just open Teams on the phone. Okay, so it's basically a way for us to avoid writing every time all the elements of the list. So we just give them names, and so whenever we want to play around with these lists, we just call the lists by their name. Okay? And let me show you what I mean by this. I'm going to open a Jupyter notebook. Okay, I'm gonna run this cell. So you see here I'm going to define simultaneously this list with Portuguese words called Portuguese and this list with English words called English. I have defined them, and now you see nothing happened when I run the cell. Nothing ever happens because I'm just defining things. So now if I write Portuguese and I press play, if I run the cell, the computer will tell me the corresponding list. Okay, so it's like I'm calling Portuguese, and the list hears its name, and the computer returns the elements. And the same happens if I write English. If I call English, where are you? I will see the list that English defines. Okay.
Every time we do this, okay, so uh, don't please don't forget that we are talking about a language that explores a functional parallel. So when we have something like this, so these kinds of expressions, we are just saying that these Portuguese name is now equal to the list of words. Okay, so this means that we can now use Portuguese and English instead of the list itself. Okay, it's not a variable in the sense, in the imperative sense, you know. It's just names that are identifying something.
Thank you, Luis. So the question is, how can we relate these two lists to create a mini dictionary, Portuguese-English mini dictionary? Do you have any idea what operation can we use?
Again, we have two objects, so two lists. So what do you think that we can do with these two lists in order to create a dictionary? So just an int, okay? So we are talking about getting a list that creates the correspondences between words in Portuguese and words in English.
Well, I think we can reveal the answer. So we are going to use the pairing list operation, the zip operation, okay? So if I do Portuguese and then I pair it with the list English, I will obtain precisely a list of pairs. And in each pair, the first component is the word in Portuguese, and the second component is the respective English translation, okay? So, gato, cat, casa, house, ovo, egg, raposa, fox. Okay, it makes sense. So, gato, cat, casa, house, ovo, egg, and raposa, fox. So basically, we have these pairs, and we have first the Portuguese word, and second, the English word. Now, what happens if I press play here in this cell? When I run this cell, what will I get? If I pair English with Portuguese, what will the difference be? What kind of dictionary will I obtain?
Yes, so what will we get when we do this now? Any hint? Any suggestion? No, Yasmin. No. Well, we are talking about two lists that are zipped. And so the result will be once again a list. But what are now the elements of this list?
Yeah, it's more or less like in each pair, the order of the words will be reversed. So that's correct, you see. For instance, here, cat appears first and then gato. Okay, so and then here house appears first and then casa, whereas here we have casa first. So now this is a sort of dictionary that translates English words to Portuguese ones. So it does the opposite, the inverse of the previous one. Makes sense? I'm going to switch to PowerPoint.
Don't forget that every time we are talking about a pair of elements, there is also a sequence, an order, okay, in the elements. So the left element indicates that we can then associate with the element on the right. Okay, so in a sense, we are also modeling the arrow, the correspondence between the words in Portuguese and English in one direction to the other. So starting in Portuguese to English, or vice versa. Okay, so we may start with the word in English and then to to associate that word with the Portuguese word.
Yeah, so using the zipper analogy is like we have, Portuguese words on the left, starting with gato. So the zipper works from down to top, from bottom to top. And so when we zip them, we will pair these meanings. So each meaning on the left will be paired, each word on the left will be paired with its translation or meaning in English on the right. And if we switch the order of the lists, it means that each English word will be paired with the corresponding translation in Portuguese. That's the difference. Okay. And as we have seen before, this operation is not commutative, okay? And it's also not associative. This was the last thing that we saw in our morning session, if you remember. And again, you can see by the previous example, that the operation is indeed not commutative because Portuguese paired with English is distant, it is different from English paired with Portuguese. Okay, so I will ask Luis to launch a poll, please.
Yeah. Yeah. Poll launched.
So first, you need to tell us how many pairs of meanings the dictionary has. Then how many different words in English? And finally, how many different words in Portuguese?
Okay, we already have some answers.
Yeah. So how many pairs of meanings? Well, we just need to count how many pairs are in the list. So we have the first pair, cat, felino. Then we have the second pair, cat, gato. Then the third one is egg, ovo. Then the fourth one is fox, raposa. The fifth one is house, casa. And the sixth one, the last one, is residence, casa. So we have 6 pairs of meanings. Now let's count the English words. Well, cat appears twice, okay? So that's just one word, cat. Then we have egg, then fox, then house, and then residence. So there are 5 different English words. And most of you wrote, thought that they were 6, okay? But they are not 6 different words. They are 6 in total, but we have repetitions. And there are also only 5 different words in Portuguese, namely felino, gato, ovo, raposa, and casa. The last 2 are the same. So these were the correct answers, 6, 5, and 5. All right. So now there are words with more than one meaning. For instance, the English word gato can mean felino. The English word cat can mean felino or gato. Okay, so we have these 2 different meanings. Now what we are going to do is we are going to use a diagram with arrows to represent each pair of words. So on the left, we have English words, and then on the right, we have Portuguese words. And an arrow connects an English word to the Portuguese to one of its Portuguese meanings or translations. And observe here that cat has 2 different meanings, gato or felino. But what if we want to group the different meanings of the English word? What if we want to register that cat can mean both gato and felino? How would we do that? So we can create a list with all the possible meanings. So please take a look at the difference between these two diagrams. Here in the diagram on the right, you can see that cat has two arrows leaving it. Gato and felino, two meanings. But here on this left diagram, there's only one arrow leaving each name on the left. Why? Because we group in a single list both meanings of cat, both gato and felino. Okay? So this is a way of grouping together the same meanings of a single word, and we have all the information there. And there is a function that we defined in Haskell called collect that collects all the meanings of a word into a single list. Okay, so if we apply collect to these two pairs, we are going to get this. I'm going to show you just a moment. So window and then this. Okay, so let's call dic to this dictionary. Okay, I'm gonna call it that. And now if I apply the function collect to this dictionary, I'm going to get in the first component strings, and in the second component I'm going to get lists of strings which have all the meanings in Portuguese. Okay, so let me just write dic here so you can compare. So this is the original dictionary. Each element is a pair whose components are strings, but when I apply the collect function, the second components are always lists. And there is only a list with more than one element because there is only a word with more than two meanings. You see, so cat can both mean felino and gato. Therefore, when we apply the collect function, felino and gato will appear on the same list after cat because we have here all the different meanings of cat. Let's see
in
if
other
you
words, in
yeah.
other words, what you have here, again, we are talking about modeling information, okay? So we are creating, again, the model that will represent the information that we intend to explore. And the first list represents the first diagram. So it's modeling the information that is represented in the first diagram. The second one is representing the information that is represented in the second diagram. Okay.
Yeah, so now to check that you understood this collect function, I would please ask Luis to launch this poll. And now we are going to work with different lists. So we will have a mini dictionary with words in the language of elves. So if you like Lord of the Rings, you will enjoy this exercise. So we have these words in Elvish, Erister, Bin, Lurlith, Nor, I have no idea how they're pronounced. And then we have a list with words in English with the translations, okay? So Erister means teacher, Bin means young man, Lurlith means boy, also means boy, so we have to. It has two different meanings, and then Lurlith is sky, and Nor is love. Okay, so I'm going to,
So you want me to
tell the
launch the
computer.
poll, Ines?
Yeah. So this is Elvish and this is English. And now please launch the poll, which is about these two lists.
Yeah. So the poll is already there. So you can now answer. This is activity number 11. And you have 2 questions on this poll. Okay, I already have some answers.
Yeah. Okay, so everybody got the first one right. Okay, so oh yeah, this one. So if we collect these, we'll have a list with 2 words here in bin, okay, and all the other lists will have only a word because these are words with only one meaning. The only word with more than one meaning is bin, which can mean either young man or boy. And so how many elements does this have? So the number of elements in this list is the number of pairs. Okay, so we have 1 pair here, 2 pairs, 3 pairs, 4 pairs. Okay, 4. So the length is 4. That's it, not 8, 4. Do you have any question regarding dictionaries? Louise, I don't know if you want to say something else.
Yeah, just that on the poll, the second question, okay, that is a trick there. So we are asking for the result of applying the zip on the Elvish
Oh yeah,
list. Okay, so it's
Elvish,
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 zip,
sorry.
Elvish. Okay. Yeah,
Yeah.
but there is no problem. So the answer is in fact the number of elements on the Elvish list. Okay.
Yeah, so it was even easier.
Yeah.
So Elvish, zip, Elvish, it's just like, you know, for every word in the original list, you have a pair with whose components are that word. So
Yeah.
since we have,
Yeah, but
you see,
then
so
by
now
applying,
we
yeah,
collect.
collect, and then okay, so by applying collect, then since we have the 2 times the bin, okay, so then we'll have a shorter list in terms of number of elements, and so we have the final answer.
Yeah, so let's compare. Let's see this step by step. So Elvish, Elvish. Okay, you see here we have bin, 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 bin. When we apply collect, we're going to say, okay, bin means bin, just bin. So this is redundant. We have the same information twice, and applying collect allows us to get rid of that. So only these actually matters. Okay? All right. So I believe we can move on.
Yeah.
Okay, so I'm going to share my screen. All right, so now we are going to talk about graphs. Very well, and we'll first speak about unlabeled graphs. Now, as you may have noticed, we are surrounded by several networks and connections. It's like everything is connected. For instance, houses are connected by roads, telephone poles are connected by cables, many people are connected through social networks, and so much more. So there are these connections established everywhere around us, and I have a challenge for you. Can you guess what the following image represents? Those who have attended our session regarding the second cycle have already seen this in the webinar, but we promise that on the last part of this session, we have something different. So after graphs, we have something that none of you have ever seen before. So I'm going to zoom in to help you. Okay, so what is this? What do we have here? What do these numbers mean?
That's correct, Yasmin. Yeah. IP addresses.
Exactly, these are IP addresses. So basically, what you just saw is a map or a graph of the internet. And we have several dots which represent IP addresses. And these dots, some of them are joined by lines. So this is a sort of map of the internet. And nowadays, more than 1 billion people have an Instagram account. More than 1 billion. There is so much data there. How can we organize and access so much information using our computers and mobile phones? Again, how can we model a social network like Instagram? What data structure should we use? How should we deal with that data? So obviously, we're going to look at an extremely simplified version, but you will see that lists are still important. Lists of pairs are going to save the day again. So this is sort of a mini Instagram. And an arrow from a person to another means that the person where the arrow starts follows the person where the arrow ends. For example, Mary follows Isabella because there is an arrow from Mary to Isabella. However, Isabella does not follow Mary because there is no arrow from Isabella to Mary. Okay? So in Instagram, you can follow a person without the person following you. Therefore, it's important that we have arrows and not just lines. These arrows must have a direction. So the person where the arrow starts follows the person where the arrow ends, but not necessarily the opposite. So basically, we are assigning a node to each user and connect to users by an arrow if one of them follows the other on Instagram. Now, in this diagram, how many pairs of friends follow each other? So how many pairs of friends are mutual followers? Meaning that A follows B and B also follows A. Luis, if you can launch the poll.
You already have the poll there.
All right, we already have some answers. So I think I'm going to reveal the answer. And as you can see, we have 3 pairs of friends that follow each other. Okay, so Mary and Ryan, Ryan and Jane, and Isabella and Peter. These are the only cases where we have one arrow going from a person to another, and also the arrow in the opposite direction. So one follows the other and the other follows the other. Okay, so we only have 3 pairs of mutual followers. And structures of this kind are called graphs, and they are super useful for visualizing relationships between things. But how do we represent them on a computer? So this is a graphical representation, it's just a drawing with arrows and nodes, but how do we represent this on the computer? Well, again, we can use lists of pairs. For instance, the pair Mary-Ryan is on the list because Mary follows Ryan. And the pair Mary-Jane is not on the list because Mary does not follow Jane. Okay? So a pair AB is on the list if and only if A follows B. Now, the question is, looking at this list here, what pair of friends is missing from this list? Luis, if you can please launch the poll.
Launched.
Okay. So let's see if we get some more answers. So you see there's only a missing pair. All the others are already here. And if you look closely, you see that Peter follows Isabella, but the pair Peter-Isabella is not here. Okay, so none of these pairs starts with Peter, yet Peter follows Isabella. So that's the missing pair. Okay, this green arrow was the missing one. All right, so now that we have spoken about unlabeled graphs, we are now going to talk about labeled graphs. And what's the difference? Well, suppose that we have the same social network. Suppose that this is Instagram, but now these arrows have more information. They register the year that one person started following another. For instance, by looking at this, we see that Mary started following Isabella in 2018. And Mary started following Ryan in 2021. And Jane started following Peter in 2020. Okay, so numbers on the arrows mean the year that the person started following another person. So this graph contains more information than the previous one. And now, using a list, how can we represent this labeled graph on the computer? We are still going to use pairs, but now we have more information. So how are we going to add that information into our list? Well, obviously we could have different approaches, but here's what we're going to do. We are going to consider a list of pairs, and each element is going to be a pair, like this one here. Like this one here. And the first component of each pair is going to be a pair of friends, where the first friend follows the second. And the second component is going to be the year that a friend started following another. So in this case, what pair is missing from the list below? Luis, if you could please launch the poll.
Yeah. Justin, if you look at the years, you can easily see what's missing.
Okay, so we already have some answers and they are all correct. Congratulations. So the missing pair is Peter-Isabella 2016, meaning that Peter started following Isabella in 2016. Okay. Now, let's take a look at a slightly different graph. So this is no longer models a social network. Imagine that Ryan wants to build a house, okay? And here is the graph of the construction work involved in building that house. And what do the arrows mean? For example, this red arrow going from walls to roof with the number 5 means that the walls will take 5 weeks to erect, and the roof can only be placed when the walls are finished. Okay, so the number indicates the time that a certain part of the house takes to build, and the arrows means that we can only build some stuff after we have already built other stuff. For instance, we can only place doors after we have erected the walls. And we can only paint the house after we have doors, roof, and a floor. Okay? So that is the meaning of these arrows. So I will ask Luis to launch the poll.
Okay.
And the question is, so we have 3 questions, actually.
Yeah.
And the first question is, how long will it take to build the house? So how many weeks? And then we are asking if there is any delay if the doors start to be made 2 weeks after the walls. And last, the carpenters want to make the doors as soon as possible and place them as soon as they are ready. Can they do that? Okay, so we already have some answers. So the total duration of the work is 11 weeks. Why? Because we need 5 weeks to erect the walls, and then the roof takes another 4 weeks, and then painting takes 2 weeks. So 5 plus 4 plus 2, 11. And that really is the total duration. It cannot be less because you cannot put the roof before you have the walls. Okay? Then regarding the second question, if there is any delay if the doors start to be made 2 weeks after the walls. No, because the doors can only be placed 5 weeks after the walls are erected. And the doors take only 1 week to make. Okay? So we can wait 2 weeks and then start building the doors, and then we still have to wait and we still have time to place the doors. So there is no delay. However, the carpenters cannot place the doors as soon as possible, precisely because the walls take 5 weeks to erect, and we can only place the doors after we have the walls. We cannot place the doors after just 1 week. We need to wait 5 weeks. Okay? So congratulations, because everybody got this right. Now we are going to talk about road trips and itineraries. I don't know if you like to travel, I hope so. So a graph whose labels are numbers is called a weighted graph, and sometimes these numbers are called the weights of the graph or the weights of the arrows. And since the labels are numbers, we can do calculations with them. We can sum them, we can multiply them, and so on. In this graph, the numbers are distances between cities in kilometers. For instance, the arrow from Porto to Coimbra with number 124 means that we have to drive 125 kilometers to go from Porto to Coimbra. And the arrow from Porto to Viseu with number 127 means that we have to drive 127 kilometers to go from Porto to Viseu. Now, what if we want to go from Porto to Coimbra, okay, Porto to Coimbra, but we want to stop at Viseu. Then we must do Porto Viseu and then Viseu Coimbra. So we need to drive 127 kilometers until Viseu, and then another 23 kilometers to Coimbra. And so the distance is then 127 plus 93, which is 220 kilometers. Okay, so if you go from Porto to Coimbra, stopping at Viseu. Now, suppose you want to do the trip that appears here on the map. We want to go from Bragança to Lisboa, stopping at Porto, Viseu, Coimbra, Porto Alegre, and Porto Alegre. Okay? So, what list may represent this itinerary containing both the cities and the distances? Again, we are talking about a list of pairs, just like we used in social networks when we have the years, okay? So again, we have a list of pairs, and the first component of each pair is a pair of cities, and the second component is the distance between those cities. So we can use this list to represent this itinerary. 210 kilometers from Bragança to Porto, 127 from Porto to Viseu, 93 from Viseu to Coimbra, 172 from Coimbra to Porto Alegre, and 227 from Porto Alegre to Lisboa. What's the question now? So we are giving the name itinerary, okay, to this list, and our goal is to instruct the computer to calculate the total distance of the trip. Do you think that I can simply apply the function sum to this list? Let's try that. We may try it. So I'm going to go over to Jupyter. I'm going to execute this cell. Okay. So here I have already the cities defined, and I have my itinerary. You see, it's a list of pairs. What do you think will happen if I do itinerary and then sum? What will happen? So our goal now is to compute the total distance, okay? Does this yield the total distance traveled? That's my question. Will this work? Will this compute the sum of these distances? Yes or no? No, exactly. No, because it gives error. And why do we get an error? Because this is not a list of numbers. This is a list of pairs. We cannot directly sum pairs. Sum only operates with numeric lists, and this is not a numeric list. So we need a strategy to solve this problem. And what will we do? What will we do? So I'm going to add over to the PowerPoint again. And now the strategy will be the following. So first, we want to move from this list of pairs to the list with only the distances between the cities. Okay? I want to use this first list to get a list with only the distances. And then I want to add up or sum all the elements of this numeric list in order to get the result I want. So starting with the list itinerary, which is a list of pairs with pairs inside pairs, how can we get this numeric list with the distances between the cities? We need some new functions. So each element in this list is a pair, meaning that it has a first component on the left and a second component on the right. Okay? And in the computer, the first component is given by fst, so it's a function called fst. So the first component of this pair yields Porto-Visio, and the second component is given by the function snd. Okay, so fst abbreviates first and snd abbreviates second. All right, so this is the second component, 127. Now let me show you this on the computer. So first component of Porto-Visio 127 is Porto-Visio. Okay, so that's what's on the left side of the comma. And the second component is what we have on the right side of the comma, so 127. Okay? So I will ask Luis to please launch this poll, and I'm going to take a look at your answers. So we have four questions, okay? Okay, so we already have plenty of answers and they are all correct. So I think you got this. So Porto-Visio first is Porto, Porto-Visio second is Viseu, Viseu Coimbra 93 is Viseu Coimbra, and Viseu Coimbra 93 second is 93. Okay, so now that you know this, I will ask Luis to launch another poll. So you must select the expression that allows us to obtain the list of distances, using the knowledge that you acquired in the morning session.
Okay, poll 17 launched.
So what expression allows us to obtain this list? Even if you can't see the poll, try to come out with the expression. So we start with this list itinerary, and then what function or functions should we apply in order to get only the first components of each pair? Okay, so 70%, 75% of correct answers in this one. So it is precisely itinerary map second, okay? Oh, unfortunately, we have some people who can't see the poll. But yeah, map second is correct, okay? Because we want to go to each element of the list and we want only to extract the second component. So we are going to apply second to every element of the list, okay? Because the numbers appear in the second components, okay? So we want these and these and these and these and these. And the second, these numbers are precisely the second component of each of these pairs. And map is the function that allows us to apply a function to every element in a list. So that's it. Okay. And we apologize for some people not being able to see the polls.
Yeah. Yeah, it's something related with the browser that
The
is
browser,
blocking
yeah.
something.
Okay, so now to end this part, one last activity. So now that we have this list, the computer only needs to sum all these numbers, right? Now we have a list of numbers, we only need to compute their sum. What is the complete computer program that allows us to reach our goal? So please select the expression, please launch the poll, and then please select the expression that does what we want. Okay, so we already have some right answers, and the answer is simply this. Okay, so we have itinerary, then we apply map second in order to get this list with only the numbers, so the distances between the cities, and then we apply function sum to compute the sum, and we get 829. So I'm going to switch to PowerPoint. Okay, so let me just summarize what we did. Okay, so we wanted to list all the second components of the pairs, and for that we wanted to apply the function second to every pair in the list. And for that we used map. Okay, so we started with our list itinerary, and then we applied map second to get only the second components, which are the distances between the cities. And then we only needed to sum all the numbers in this list. And for that, we applied function sum. So this is the complete program. Itinerary, apply map second, apply sum. So with this extremely simple program, that's just a short line, okay, we could solve this problem of computing the distances between these cities, okay? So it's a very simple solution using just a couple of functions. And this is the power of Haskell and functional programming languages, because functions and composing functions is really powerful. And so, yeah, the distance of this itinerary could have been calculated by hand, but if there were hundreds or thousands of cities, only a computer could save us. So it's important that we have algorithms and tools that allows us to compute these total distances in an itinerary. Any question?
So it's now important, just before getting your questions or anything else. Okay, so just to summarize everything that we have done until now. Okay, so you have noticed that lists are really important, and just by adding to the list also the concept of pair, and at the same time also some simple functions on both lists and also on pairs. For instance, the first and second function on pairs that are also called selectors. Okay, we have been playing with these concepts in the very different ways. Okay, so we have modeling the internet, we have modeling a social network like Instagram. Okay, we were now playing a little bit with maps and so on. Okay, so the difference now for what we have done here and for when we are talking about real problems is the amount of information we are dealing with. Okay, so don't forget that when we are talking about lists, for instance, lists are the basic elements of the databases. Okay, so every time we have a table in a relational database, we are talking about rows that are in fact a list of lists. Okay,
Oops.
and so only by dealing with these some basic concepts, as I've said, okay, we have been able to model different kinds of problems to solve different kinds of questions that we were putting on those models, and with the very simple expressions, like Ines also has said, um, you were solving problems. And the most important part of also of this is that by solving small pieces of these problems, you may then easily combine these different solutions, okay, and combine these different expressions in order to solve a bigger problem. Okay, so that's why we are always talking here about what is popular to now at this moment to say about computational thinking. Okay, so we are applying computational thinking just because we are trying to find the best models. Then we are trying to apply functionality, or in other words, algorithms to those models. And with that, we are solving problems. The other thing that is also important is that diagrams are really, really important. Okay, so tables and diagrams are in fact the most important tools that we have in order to express our thoughts. Okay, and the good thing with diagrams is that you can easily find patterns when we are trying to draw different diagrams to solve different problems, because in a diagram you can easily see, and you can see more easily the patterns that you are trying to find and you are dealing with. When we are talking about then a programming language like Haskell, and when you are exploring the functional paradigm, you can more easily deal with those patterns and to find the best solutions by reusing things that you have done in the past. And this is really powerful. Okay, that's precisely one of the most important things when you do programming, and when you use a programming language to solve real problems, is to try to reuse, try to find patterns that in somehow solve specific parts of problems that you have been dealing with. Okay, if you go for some other languages and also other paradigms. So the most popular one is, of course, the object-oriented paradigm, which is in fact very important, especially when we are dealing with very large systems. Okay, we are not just talking about programs, we are talking about software systems. Of course, that the web-to-object-oriented paradigm is very useful and very powerful as well. We are dealing with usability, we are dealing with human machine interfaces and so on. Okay, but at the end, you want to solve the core of the problem you are dealing with. Okay, and that's why nowadays we usually have and use programming languages that are capable of dealing with multiple paradigms. Okay, and the functional paradigm is in fact the most powerful when you are talking about solving the problem and solving the core of a problem that you are facing and trying to solve. Okay, that's precisely what have been done here. Okay, so we are not dealing with interfaces and so on. We are just focused on the problem, and we are just trying to solve the problem in a more efficient and easy way we can. So I don't know if you have any question, not only related with the problems that we have solved here, but also with any other topic you want to discuss now. Well, if not, we'll jump now for the final part of this session.
No, I think we should do a break before the
final
part.
after the break, sure. But after the break, we'll also deal and show you how we can easily deal with if then else expressions. And again, when we are talking about these expressions in a language like Haskell or in the functional paradigm, or in other words, in a more rigorous way, we can see that we cannot do, or we should not do, everything with the if then else. Okay, we should follow some strict rules that, if applied, are really powerful, because we take full control of what we are doing when we are applying if then else expressions. Okay, and by the way, by applying if then else expressions in the wrong way is probably one of the most it's probably one of the ways that programmers are always dealing with bugs. Okay, is because they are using these control structures and control flows without following some specific and strict rules that must be applied in order to avoid side effects, or in other words, bugs. No, thank you, Mark. And we really hope that everything that we are discussing here can be helpful in any way. And in specifically, again, the questionnaire that we will put in your hands at the end of this session will precisely try to understand also from your point of view if all this makes sense when we are talking about teaching young students, and if all this makes sense for you in terms of when you are preparing these kind of sessions to teach students the basic concepts of computer science, and in particular of programming.
Okay, so I think we'll now take a 15-minute break.
Yeah.
So see you at the time zone.
Yeah, 15 minutes from now. Yeah, that's okay. That's right.
See you soon.
See you soon. Okay, here we are again. Final stage.
Is everybody back?
Well, I think so. Let's check. Okay, we'll just wait 1 or 2 minutes and then we will restart. Everybody there?
I think maybe we should start.
Yeah.
Although
Yeah, I
we
think
have
so.
no answers.
Yeah. Hello? May we restart?
Cri.
Okay.
One answer.
Thank you, Mark.
Yeah.
So we'll now proceed to the final stage, last
Yeah.
part,
Last mile.
last mile, but an
Last
important one.
mile. Okay, so let's go to Jupyter. I'm gonna run these. Okay, so as we said, we are now going to talk about Boolean values, conditional expressions, alternative transformations, and all that stuff. And to motivate all of these, I want to start asking you, do you want to be a millionaire? Would you like to win $1 million? Well, our students would like to, indeed. And I don't know if you're familiar with the millennial prize problems, but they are these really difficult math problems. And there are prizes for those who can solve them. And some of these prizes are like $1 million or something close to that. And there's a problem which has been unsolved for decades. That is not a Millennium Prize problem, but is very interesting. And the Japanese company offers almost $1 million to those, to anyone who finally solves this problem, which is called the Collatz conjecture. So we will think of this as a game, and this game consists of the following. You think of a positive integer, and then if the number is even, you divide it by 2. If it's odd, you multiply it by 3 and then add 1. Then you repeat this process with each new number you obtain. And if you reach 1, you can stop. So if we model this game using a list, we will get a list of numbers, right? We start with a number, then we either divide it by 2 or multiply by 3 and add 1. Then again, we either divide it by 2 or multiply it by 3 and then add 1, and so on, okay? So for example, if our first number is 5, if I think of number 5, then because 5 is odd, I'm going to multiply it by 3 and add 1. 5 times 3 is 15. 15 plus 1 is 16, so I get 16. Then, since 16 is even, I'm going to divide it by 2, and I will get 8. Then I will divide 8 by 2 and get 4. Then I divide 4 by 2 and I get 2. And finally, I divide 2 by 2 and get 1. Once I reach 1, I can stop. So the game has these two very simple rules. If it's odd, multiply by 3 and add 1. If it's even, divide by 2. Now, here I already wrote a program which I called Collatz sec, okay? Which gives precisely this list, okay? And some numbers have a short list, other numbers have, a bigger list, but in both cases you can see that we reached number 1. So number 1 is the last one, and here number 1 is also the last one. This little game gave rise to a conjecture. So the Collatz conjecture is a famous problem that remains unsolved for more than 85 years. And it asks the following question. Is it true that by playing the previous numerical game, you always reach number 1? Or is there some number that you start with and after doing these transformations, you never reach number 1? Can you avoid number 1, or will you always end up there? Mathematicians believe that this is always the case. So for years, we believe that you always end up in number 1. And computers have already shown that if you start with any number less than 300 sextillion, you always arrive at number 1. So we have all these empirical data, and everybody believes that it reached number 1, but no one can explain why. No one can provide a rigorous mathematical proof to why this is true. So this is a very famous conjecture and one of those problems that prevents mathematicians from sleeping at night. Now, we too will try to program the computer to help us analyze this problem, okay? So our goal in the next minutes will be to end up with a program that takes as input a number and produces the list, the numeric list, with all the numbers that we obtain by playing this Collatz game. and it will take some time. We will sort of take a long tour until we get there, but it will be worth it. So the first thing is we need to determine whether or not a given number is even or odd. And on the computer, there are two functions, again, functions, even and odd, that allows us to do that, okay? For instance, if I write 2 even, the result will be true, because it is true that 2 is an even number. It is divisible by 2. However, if I execute 5 even, then the result will be false, because 5 is not an even number. 5 is an odd number. So now executing or applying the function odd to number 5, the result will be true. It's true that 5 is an odd number. Okay? Very simple. So again, using our arrow diagrams, we can think of, writing the number on the left. And then we have a function which is like asking a question, which is like, is this even? And the result is either true or false. Or, is this odd? And the result is again true or false. So we do not write this question mark, okay? We would get a mistake, an error, if we had written it this way. But in our heads, we think that we are asking a question. We are asking a question whose answer is either true or false. Or we can either think that we are politicians affirming 5 is odd, and the computer is saying that's true, or we are politicians saying 5 is even, and the computer is saying that's false. Kind of think whatever you want. Now, so far we have worked with some data types, namely numbers, characters, numeric lists, strings, and so on. But it's the first time that we are dealing with true and false. Okay, so what are true and false? Is true a number? Is it a character? Is it a string? No, it's none of those. We are dealing with a new data type. And how will we call this new data type? The values true and false are called booleans or boolean values, and they were named after the mathematician George Boole. Boole worked in something now called the Boolean algebra. So he studied these operations and this arithmetic that you can do using the values true or false. And this is really important in computing because computer is binary, and logic is also very important in computer science. So propositions and predicates are very important. So this work of George Boole really helped when humanity came up with computers. And now I'm going to ask Haskell, what is the type of these true, okay, of true? And for that, I can use this colon and then write a T, and then the thing that I want to know, the type, whose type I want to know. So C is going to tell me true is a Boolean. So he writes bool, okay, shortens Boolean to bool. So he's going to tell me, is telling me that true is a Boolean value. And I can do the same for false. So the type of false is also a Boolean, okay? So these are these new data types that we are working, this is a new data type that we are working with. Those elements are true and false. And what is a proposition? Well, a proposition is precisely a statement that is either true or false. For example, today is Tuesday is a proposition whose Boolean value is true. Today is Wednesday is also a proposition, but now its logical value or Boolean value is false because today is not Wednesday, it's Tuesday. However, if I say something like, do you like football? This is not a proposition. This is not something that is either true or false. It doesn't have a truth value, okay? It's just a question, so it's not a proposition. Okay, so propositions are statements that are either true or false. But how do we write propositions in the way that the computer understands? How do we write these propositions or some common propositions using the computer? Let's see. So suppose we have the proposition 2 is greater than 5. How can we write this? Well, again, thinking in terms of functions, we can think in the function greater than 5 and apply that function to 2. And the output will be false because 2 is not greater than 5. Let's see. So I have 2 and I have this function greater than 5 whose output is either true or false, and I'm going to press play and the result will be false. So the computer is telling me it's false that 2 is greater than 5. So if somebody says 2 is greater than 5, the computer will say, no, that's false. Okay? And again, we can imagine an arrow asking the question, is 2 greater than 5? False. Okay? No, that's false. That's how it works. Another proposition. Suppose that we want to ask the computer if the character A, how do you say minúscula?
Lowercase.
Lowercase, yeah. So we want to ask if the character lowercase a is equal to the character
Uppercase
A.
Yeah.
And how do we do this? Now we are going to consider the function equal a. Okay? So this is a transformation that allows us to determine if a character is equal to a. So we are asking, is lowercase a equal to uppercase a? Now, if we had written is lowercase a equal to lowercase a instead, the answer would be true. But this first one is false because a, lowercase a, is not the same character as uppercase a. They represent the same letter, but not the same symbol. It's not the same character. However, it's obvious that a character is equal to itself, so this will be true. Okay, so this is how we write this proposition. Is lowercase a equal to uppercase A? And again, we have the corresponding diagrams. The first one yields false, the second one yields true. Now, let's see this proposition. The list 5 to 3 has 3 elements. Is this true or false? Well, the number of elements in this list or sequence, sometimes we write sequence meaning list, so sequence and list in computation is the same thing. So the number of elements in this sequence is given by 5 to 3 and then an arrow length. Okay, so it's the length of 5 to 3. Now, if we want to know if this list has 3 elements, then we do 5 to 3, we compute its length, and then we ask the computer if that's equal to 3. So we finish off with the transformation equals 3, which is written equal 3. Let's see. So the result is true, because 5 to 3 has indeed 3 elements. And this is our diagram. So first, I apply function length to determine the length, so the number of elements of the list. And then I ask if the number that I obtain is equal to 3. And the answer is true because I have 3 numbers, 5, 2, and 3. And finally, as we have already seen, if I want to know if number 4 is even, I can just apply function even. And if I want to know if number 42 is odd, I can just apply function odd. So for even, we'll give true, and 22 odd yields false. Make sense?
Yep.
Okay, so I think you're ready to test your knowledge. So Luis, I would ask you if you can please launch this poll.
Yeah, just 1 second. And no, sorry.
I will launch it.
No. It's
It appeared closed,
okay.
but I already launched it.
Okay. Thank you.
For some reason, I can already see the answers.
Yeah.
What's
Me
wrong
too.
with this?
I don't know. Yeah, the answers are already here. I don't know why.
Can you also see the answers? You can't see the answers, but
Yeah.
can you reply? Because we can't reply.
You can reply if you choose the back to question option.
Oh, okay.
Yeah.
Thank you. Let's just wait a few more seconds.
Yep.
Okay, so the first one, we are asking if 22 is less than 33. Is this true? Is 22 less than 33? Well, yes, it is. So the answer will be true. Then we are asking if by removing the duplicates of this list, we get the list 2, 3, 2, 1. Is this true? It is not. Indeed, if I apply nub to this list, I'll get 1, 2, 3. Not this one, okay? Because nub removes duplicates. So it'll just delete this final 2, and the rest will stay the same. Now, in the third one, we are asking if the length of insiku is less than 10. So we are asking whether or not insiku is less than 10 letters. Is it true? Yes, because insiku has 6 letters. So if I execute this program, the result will be true. Indeed, if I write this, I'll get 6. And 6 is indeed less than 10. Now, the last one is asking if the maximum of this list, so if the element with the greatest value is 3. Is it true? Yes, it is. So the greatest element is 3. So the maximum of the list is equal to 3. Any questions so far? Are you following up? Does it make sense?
Okay. Now, okay. So now we'll apply this concept to the if then else expressions, okay?
Okay, so we will move on to conditional expressions or if then else expressions if you are familiar with those. So recall the number game associated with the Collatz conjecture. You think of a positive integer, and then if the number is even, you divide it by 2. If it's not, you multiply it by 3 and then add 1. Okay, and you should repeat this process with each result you get. If you reach 1, you can stop. This is the famous Collatz conjecture. So the question is, can you always reach 1? But this is just like a game, okay? So you will get a sequence ending in 1. Let's assume that you always reach 1, as everybody believes. Now, each step of the game can be described as follows. If the number is even, then apply the transformation divide by 2. Else, apply the transformation, multiply by 3, and add 1. Now, what is the proposition and what are the transformations here? Can you tell me? What is the proposition and what are the transformations? I would like you to write in the chat if you don't mind. If a certain proposition is true, then apply some transformation, else apply another transformation. In this case, what is the proposition and what are the transformations or functions? So the proposition is the number is even. It's what what appears after if. So after if we have the number is even, and that is our proposition. And then the transformations are what follows after then and after else. Okay, so the transformations are divide by 2 and multiply by 3 and add 1. So this is what we are dealing with. So note that the computer transforms the starting number in different ways depending on whether it is even or odd. If the number is even, then we apply some transformation. If the number is odd, we apply another transformation. So it's like there are two paths along the road, and the computer chooses the path according to the Boolean value or logical value of the proposition. So everything depends on the Boolean value of the proposition, the number is even. That's what we need to study. And these expressions with the structure if then else are very useful and frequent in computing, but they are also widely used in our daily lives. For instance, in the movie Beauty and the Beast, if the monster loves and is loved, so this is the proposition, then it becomes a human, so it is transformed in the human. Else, it remains a beast forever. Else, it is transformed in a beast. Okay? And in this way, these expressions with the structure if then else allow us to apply transformations in an alternative way. Meaning that if the proposition is true, then a certain transformation is applied. If the proposition is false, then another transformation is applied. And we picture this in this diagram on the right. So we sort of take a proposition as input, and the Boolean value or logical value of that proposition can either be true, in which case we apply transformation 1, or false, in each case we apply transformation 2. So to check if you understood this, I will please ask Luis to launch this poll.
Yep. Okay. Right.
Okay, somebody's saying the poll is covering the screen. Let me explain you something. So you see, the poll is indeed covering this part of the screen. So what you should do is you should close it. Okay, close it, click on close. And then you should click here where it says polls. And if you can't find it here, it should appear here. But if you can find it here, click on polls. And then you will see the polls on the right. Okay? And you can answer on the right. Okay? Here. Okay, so how does this program work? We are saying if the length of the list 8 to 2 is even, so if the list has an even number of elements, then apply function maximum, else apply function sum. So the first thing we have to know is, does this list have an even length? Does it have an even number of elements? How many elements does it have? Well, this list has 3 elements, and 3 is not an even number. 3 is an odd number. So the Boolean value of this proposition is false, okay? So if it is false, then we skip to the else expression. Because if it's even, then we would apply maximum, as you see on the diagram on the right. But it's not even, so we are not going to apply maximum, we are going to apply sum. And what is the result of the sum of 8, 2, and 2? Well, 8 plus 2 is 10, plus 2 is 12. So the output is going to be 12. Okay? Let's see this step by step. So first, let's see what's the Boolean value of this proposition. It's false. If this is false, then we are going to skip to this else part. And the result will be this. So this 12. Okay? precisely the result of this program. Does anybody have any question? Does this make sense?
Yep. Okay.
Okay. So here you can see this diagram. So the input sort of is 822. Then we ask if the length is even, and since the answer is false, the result will be 12 because we will compute the sum, not the maximum. Now, note that in the previous example, the transformations maximum and sum are of the same type. That is, they both transform a numeric list into a number. So maximum takes as inputs a numeric list and outputs a number. And sum also takes as inputs a numeric list and outputs a number. Okay? And this is a requirement in Haskell, in this specific programming language. This is a requirement. You can only deal with transformations of the same type. Okay? They must output the same type of data. In this case, the output is a number. Okay? For instance, this program here will not work because the transformations are sort and sum. However, sort outputs a numeric list, whereas sum outputs a number. And since a numeric list and the number are not of the same type, the program will give an error message. See? Okay. That's the problem. Sort and sum are not of the same type, and they have to be in order for an if-then-else program to work. Okay, next activity. Recall the Colette's game and consider these transformations. So if you write div2, this allows you to divide an even number by 2. So 4 div2 is 2, 6 div2 is 3, 8 div2 is 4, and so on. Then the transformation star 3 means multiplying by 3. And finally, the transformation plus 1 allows us to add 1. So now I want you to select the program that allows us to calculate the number that comes after 21 in Colette's game. And I will ask Luis.
Yeah. It's lunch.
There's a question here. Is this program as same as Python? Python has a similar if-then-else structure.
Yeah, absolutely. So any programming language, every programming language has if-then-else or control structures like this. Okay. So the only thing that matters here when we are talking about what is going on is that in fact we are, every time we have an if-then-else structure or control flow, we are getting an input as well, okay, and then the transformation needs to produce an output that is compatible in both sides. Okay, so in the then part, you will need to produce a result that has exactly the same type that of the transformation of the else part. Okay, and so the most part of the programming language are lazy on this aspect, and so they are not strict. But when we are talking about languages like Haskell, okay, that apply these rules in a very strict way, and the idea of all that is precisely to help us to take full control of the program and of the transformations that you are trying to apply.
Okay, so what is the program that allows us to calculate the number that comes after 21 in Colette's game? What is the proposition and what are the transformations? Knowing this, okay? So, not sure if you are having trouble. Okay, so we already have some answers. So the right answer is the first one, okay? So this is the complete program. If 21 is even, then we divide it by 2, else we multiply it by 3 and add 1. 21 even? In this case, the proposition is false because 21 is not even, it's odd. So we are going to multiply it by 3, getting 63, and then we add 1, which yields 64, okay? As you can see. It's very important that you understand this, otherwise you will not understand what follows, okay? So if 21 is even, then we take number 21 and we divide it by 2, else we take number 21, we multiply it by 3, and then we add 1. And since this proposition is false, because 21 is odd, we are going to move to this else part, okay? So the result is 64, precisely because 21 times 3 plus 1 is 64, okay? So the computer will execute this instruction. Okay, now we move on to alternative transformations. So we have a program that allows us to determine the number that comes after 21 in Colette's game. What would have to be changed in the program if we wanted the number that comes after 5 or after 10 or after 73? Please answer in the comments what would I have to change in this program above. Would I have to change the proposition? Would I have to change the transformations? Would I have to change the number? No answers. Okay, exactly. So I just need to change the number. So if I want to know the number that comes after 5, instead of 21, I write 5. I write 5 here, here, and here. And I execute this cell, and the result will be 16. Because 5 is not even, so the proposition is false, and therefore the computer will compute the expression that comes after else. The same happens with 10, but now 10 is even, so the computer will execute the instruction that comes after then. And finally, if we want to know the number that comes after 73, we just replace the number by 73. And since it's odd, this is false, so we will execute the condition that comes, the expression that comes after else. So in general, if we consider any number, the program is, so if the number is even, then we take the number and we divide it by 2. We apply the function divide by 2. Else, if the number is odd, we take the number, we multiply it by 3, and we add 1. So this works for any number. And then we just need to replace the number. If it's 21, then we replace number by 21. If it's 5, then we replace number by 5. If it's 10, we replace number by 10. So this is a general program. Now, the word number is a bit long, don't you think? I think so. So let's be lazy, and instead of writing number, we will just write n. Okay, so instead of number, we will just write its first letter, N. Now, if we replace number by N, we get a somehow simpler program. It does exactly the same, but it doesn't take so much space because N takes less space than number. And this is our generic program, okay? Where N is any number. We just need to replace it by whatever we want in order to get the result. Okay, so this is a diagram. If n is even, then we divide n by 2, else we multiply it by 3 and add 1. And here, n can be any number. But if we want a result, we need to replace n by some number, okay? Because imagine if I write, for instance, if I just write this with n, I will get an error message because it says, I don't know what n is. The computer does not know what n is. I need to put down a concrete number in order for it to work. Otherwise, it will not work. But if I put 17, for example, now it will work. So, in order for us not to be constantly writing if 3 is even, then blah, 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 if 4 is even, blah, 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 we write this generic program. So this program here, which we will call call@, depends on the value of the parameter. Okay? So we will write call@, n equals, if n is even, then divide it by 2, else multiply by 3 and add 1. And if I execute this, nothing happens because I'm just giving a name to a program, okay? It doesn't have any type of output. I'm just saying, hey, computer, I want you to call collapse to this thing, okay? And we say that collapse is an alternative transformation because there are two alternatives. So either the transformation divide by 2 is applied, or the transformation multiply by 3 and add 1 is applied. Okay? So that's why we call it an alternative transformation. Okay, so let's see if you understood this. I will ask Louise to please launch this poll.
Yeah, just a second. And okay.
No, we cannot move the poll. You need to close it and then click on polls and open it on the right.
Yeah, that's it.
So we already have some answers. And both instructions execute this program replacing n with 5. Okay, so when the computer sees collat's 5, here it will replace this n by 5. And so it's the same as replacing 5 here and here and here. So the computer will execute collat's 5 is the same as executing this, but with 5, oops, instead. So with 5 instead of n, 16. So collat's 5 is 16. And 5 collats also yields the same answer. Okay, so these are just two different ways of applying a function to an object. Here we are writing the function first and then the object, and this is the standard way, this is the regular way, and this is our way. We first write the object and then we apply the function. And the reason why we prefer this last notation with the arrow is because it resembles more the diagrams, the functional diagrams. Okay, so these diagrams here where you have, see where you have like an arrow with the object and the answer. Okay, so that's why we prefer these notation, but both expressions yield the same. These are just, oops, not here, not here. These are just two ways of writing exactly the same thing, okay?
Yeah, the importance of this when we are trying to explain for the first time these kind of concepts to students is that so we start with concrete examples and in this case with concrete numbers, and then we jump to a generalization of the concept. Okay, and so by generalizing the concept, instead of using the number, you will use a variable, or in this case, the correct number is the argument of the function that we are dealing with, and we have also named this particular function by naming it collats. Okay, so don't forget that we are now talking about what happened when we are dealing with abstraction. Okay, and so don't forget that we are talking about the second cycle. Okay, so which means that we are talking about kids with between 10 and 12 years old. But then when you go in Portugal for the third cycle, we'll then start dealing with the first time in math with the notion and concepts of function, and is where we deal with variables. Okay, and so that's precisely what we are doing here. We are trying to write our first program using variables, which means that we are talking about functions that are generalizing these concepts for the first time.
Yeah, n here is a variable, it is a parameter, okay? So it's a general way of, using a single program to produce many programs depending on the value that we want n to take. Now, recall that in collat's game, we apply the transformation collats until we reach number 1. because it's like we only stop when we reach 1. Otherwise, we either go on multiplying by 3 and adding 1 or dividing by 2, depending on whether the previous number is even or odd. Okay, so I will ask Luis to please launch this poll. So starting with number 5, how many times is this transformation collapse applied? So how many iterations does the game have? Then the second question is, what numeric list represents all the numbers that appear in the sequence, including the starting one? This one is easy, guys. Then the third one is, what is the output of applying collapse twice to number 5? And finally, using the transformation collapse, select the expression that allows us to arrive at 1 starting with 5. So you have 4 questions, and I would ask you to please answer all 4. These are the first 2. And these are the last 2. So whenever we have a new number, we apply function callouts. Okay, so it's like we go on applying callouts until we get 1. So everybody that answered got it right. I think I can reveal the solutions. Okay. So the transformation collapse is applied 5 times. Okay, so the first time we go from 5 to 16. The second time we go from 16 to 8. The third time we go from 8 to 4. Then 4 to 2 and 2 to 1. So collapse, 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 collapse 5 times. In fact, there are 5 arrows, and each arrow represents applying the function collapse. So the answer is 5. Then, as you can see here, the numeric list we get is 5, 16, 8, 4, 2, 1. And this is called the collapse sequence or collapse list associated with number 5. So the collapse sequence of 5 is 5, 16, 8, 4, 2, 1. And the same happens with other numbers. So we also have, for each number, we have the corresponding collapse sequence, okay? So number 3 has its own collapse sequence, and number 4 and 5 and 6 and whatever. Then 5 collapse yields 8, because if we apply collapse once, we get 16, and then by applying collapse twice, we get 8, as you can see. Okay, 8. And the expression that allows us to go from 5 to 1 is applying collapse 5 times. So if we apply collapse 5 times, we will get to 1. Collapse, 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 collapse. As you can see, if I execute this cell. Does anybody has any question? Is everything okay? Okay, great. So we are going to move on to the last part. And we are finally going to write a program that gives the collapse sequence of any number. You see, I had written a program right at the beginning. So this program called sec already gave the collect sequence, but I didn't tell you how I wrote it. And now I'm going to reveal the answer. So how can we put the computer doing this? Okay, so our mission is to write a program that takes as input a number and produces the numeric list, which is its collect sequence, as an output, okay? So for instance, if the input is 5, we want the output to be 5, 16, 8, 4, 2, 1. So it is a numeric list. So the type of our program is from a number to a numeric list. And for these, as we have seen, we need to apply the transformation collapse to each new number that appears in the sequence, okay? So we will have to iterate the transformation collapse until we get to 1. How do we do that? Well, now I'm going to kill my computer, okay? So in Haskell, we have another higher order function called iterate that takes another function and successively applies that function infinitely. It never stops, okay? So it applies its transformation forever and ever. So when I execute this cell, I'm going to apply collects to 5 and then to the result of collects 5 and then to the result of collects 5 and then to the result of collects 5 and so on, and it will never ever stop, as you can see. Okay, so it goes 5, 16, 8, 4, 2, 1, and then it will repeat 4, 2, 1, 4, 2, 1, 4, 2, 1 because it just keeps applying and it just enters this stupid loop. Okay? So I'm going to interrupt my kernel, okay? My computer is already burning because it's trying to compute an infinite sequence. And I'm going to restart the kernel. Okay. All right. Okay, so it's just computing the previous stuff. So what do we have to... No, don't do that. Okay, let me just run the first cell. I mean, not just the first cell. I need to run this. I need to run everything. Wait. Hold on. Okay, so I'm gonna run everything above this cell. So yeah, forget this. See, it stopped here. So we need to provide some sort of stopping criterion because we don't want an infinite list. We want the program to stop once we reach number. For that, we can use another transformation called take until, okay? So remember, this transformation iterate allows us to apply an infinite number of times a function to a number, producing an infinite sequence or an infinite list, okay? We'll just apply the function forever and ever to infinity and beyond. Now we need to introduce a stopping criterion, and we can use this take until proposition. And what does take until do? Well, it sort of goes on picking the elements of the list until it appears one that satisfies a certain proposition. For example, if we apply take until greater than 2 to the list 1, 2, 3, 4, we will get the list 1, 2, 3. We will list 1, 2, 3. Because we will only select the elements until we see the first element that satisfies a given proposition. And the first element that satisfies the proposition being greater than 2 is 3. So we are going to stop there, okay? Therefore, to ask the computer to select from this infinite sequence that we obtain by applying this iterate collapse to stop once we reach 1, we just need to apply now the transformation take until equals 1. Okay, so once we see an element that is equal to 1, we will stop producing new terms in the list, okay? Stop. So if I execute this, you see that it ends in 1, okay? Because I'm only taking the terms until 1 appears. So I will now please ask Luis to launch the poll.
Okay. I think
Yeah,
we
so
have
everybody got it
answers.
right.
Yeah.
Yes, so see here we have these for number 5, and now we just want to generalize this. So instead of 5, we are going to write n, and that's going to be our parameter or variable. So this is it, okay? So to obtain the collapse sequence of a number n, we start with n, then we apply function collapse successively, and we up until when we reach number 1. Okay, so now you can see that it matches what I wrote in the beginning. Okay, so finally, and in a very simple way, using just one line, we were able to write a program to produce the collapse sequence of a number. This is pretty amazing. It only takes a single line because we had already defined the collapse function before. So if we want to be fair, this actually takes 2 lines. So I should say collapse equals if n even then n divide by 2, else multiply by 3 and add 1. Okay, so now this has all the information that we need. Oops, I forgot one n here. Okay, so now we have all information that we need. So actually this program has 2 lines of code, but with 2 lines of code, we were able to do this amazing thing of computing the collapse sequence of any number. So if you want a collapse sequence of 1/400, well, collapse sequence of 400, we get this, or 1231. You know, and it goes like this. So it's really amazing. Okay, so to finish, we have one last activity. Consider now a different game, which is not a collapsed game, but a game that we call in-sequel game. So how does this game work? So you think of any number, and then if this number is odd, you add 3. If it's not, so if it's even, you multiply it by 2. And you want to repeat this process with each result you get. Stop when you reach a value greater than 1000. So the first question is, what is the numeric list that is obtained if you start with 47? So you start with 47 and you need to ask, is 47 odd? If so, then you add 3. If not, you multiply it by 2, and then you continue with the numbers that you will be obtaining. Then we will call in situ our program, and you need to select the program that gives the number that comes after a given number n when we play the in situ game. And then to test if you understood this, you should write the result of 50 in situ. And finally, you should select the expression that gives the sequence or the list that is obtained when you play this game starting with any number n. So for exercises, I would ask Luis to please launch the poll.
Yeah, the last one. Then.
Thank you. So if the number is odd, you add 3. If it's not, you multiply by 2, and you stop once you reach a value greater than 1000. And in the third exercise, you need to type the result. You need to type, it's not multiple choice. You actually need to write the number. That will give you some time. Let's just wait a few more seconds. Yeah, congrats.
Okay, I think that we have some answers.
Yeah, we can reveal the answers. Okay.
Yeah.
So the sequence is this one. We start with 47, and because 47 is odd, we add 3 and we get 50. Now 50 is even, so we multiply by 2, and then it's always even, and so we multiply by 2 until we reach a number greater than 1000, in this case 1600. Then the program is as follows. So if n is odd, then we add 3, else we multiply by 2, okay, as you can see here. And the result of 50 in SQL is the number that appears after in SQL, which is precisely 100, because 50 is even, so we will multiply it by 2. And last, to get the complete program, we take a number, we apply the SQL function, which gives the succeeding number infinitely, and then we only do that until we reach a value that's greater than 1000, okay? So if we compute 50, it's this sequence. If we compute for 14, for example, it's this sequence, and so on. Okay?
Okay.
So, yeah,
We
I don't
have
know if you want
finally
to.
reached the goal.
Yeah, I don't know if you want to add something else, Luis.
Yeah, just last topics and last thing. So I will share with you again 2 links this time. Okay, the first one is the binder that you can use if you want to exercise everything that we have done in this session. So if you now go to the binder, you will see not only the 3 topics that we have discussed in the morning, but you also have the topics that we have discussed this afternoon. Okay, so you have the complete binder already available on the same link. So if you want to do some exercises at home and so on, please feel free to use it and to do that. Okay. And last but not least, I will share now the link also that would like to ask you to fill. Okay, so it's the link for the questionnaire. It's really important to get your feedback on these sessions, not only session, the 2 sessions, the morning and afternoon session. And so please just fill the questionnaire with not only the answers to the questions, but also with comments and suggestions that you may have, and we will be very pleased if you do that. Okay, and so I think that we hope that you enjoyed the session. This was the last one. Okay, so we have completed the discussions around the innovative education in digital era. Then we have talked about how to teach these things to students from the first cycle, second cycle, and third cycle. Don't forget that the third cycle was a session focused on the Python language. Okay, it was hosted by Open University and the Cisco Network Academy. And so with this, you can see the entire methodology we are trying to apply when we are talking about teaching computing to what you call here in Portugal the basic cycle of education. Okay. So I don't know if you have any further question, but if not, both Inez and myself will say goodbye to you, and we hope to see you soon somewhere.
Yeah, thank you so much. It was a real pleasure to be here today and also in the previous sessions. And we wish you all good.
Oh yes, yes. The link and everything related with this session, as well as all the previous ones, are available in the Cisco Network Academy platform. Okay, and so everything will be there. So not only the links for the video, but also the link to the questionnaire and also the link to this Jupyter Lab environment that we have been using today. Okay, thank you so much. Take care as well.
Thank you.
Okay, bye
Bye.
bye. Bye-bye.
Take care.
Bye-bye. Take care. Thank you.